Happy Women's Day. I think today is a Women's Day, right? So today we are going to talk about assumptions. But before that, let's finish the no intercept part from Monday, because I think we have just a small part left for today. So remember when we estimated the coefficients in regression, we always saw that there is an intercept estimated for each model, right? However, sometimes we may have a model that has no intercept. So when would that happen? For example, it is possible that the intercept that you find is not significant. So remember, in backward elimination, we want to just remove the non-significant coefficients and run the model again, right? That's one possibility. Another possibility is that theoretically, or from some economic principles, you may know that the intercept must be 0 for this model. You know that the intercept is always 0. So in those cases, you want to force R to give you a model with no intercept. These cases happen very rarely, but anyway, we have to know about them. We have to be aware of them. Let's look at this example. We have packages delivered as a function of expected packages delivered. So when we look at the scatter plot, we see that the two variables are correlated significantly. Yeah, there is a linear relationship between these two variables. And we can guess that the line that would represent this trend would pass through the crossing point, origin, right? We can guess that. You see here, the line is like passing through the origin. It makes sense. Do you think the line should pass the origin? Let's look at the variables. What variables do you have? We have packages delivered versus expected packages delivered. So if I have no expectation for any package to be delivered, I expect no packages to be delivered today. Probably the number of packages delivered would be 0. Most likely the number of packages delivered would be 0. On average, on the days that the expected number of packages delivered is 0, on average, the number of packages actually delivered would be 0. That makes total sense. So we looked at the scatter plot and we made some reasoning and we decided that, okay, we are gonna force B0 to be 0. We are forcing B0 to be 0. How can we do that? Remember, this is the model with intercept, or the model that allows for having an intercept, right? So in this model, we had the dependent variable tilde the independent variable, right? Now we have this model with no intercept. We are forcing the intercept to be 0. How do we do that? We are saying dependent variable tilde 0 plus the independent variable. So when we put 0 plus, that means what? That means the intercept must be 0. We are forcing the intercept to be 0. Okay. So the result of the first model would be two coefficients. One would be the intercept, which is significant, and the other is with one intercept. It does not even estimate the intercept for us. One coefficient. The first one is with two coefficients. One of them is the intercept, and the other one is with one coefficient, and it does not even try to estimate the intercept. So, by the way, you probably noticed that the coefficient for the expected package delivered, or the coefficient for the predictor, is different between these two models. So when we force the intercept to be 0, we get a different slope for the predictor. We get a different coefficient for the predictor, right? So let's compare the R-squared values. The R-squared value for the original model is 72%. The R-squared value for the model with no intercept is 99. So almost 100%. So that means we improved the model tremendously by removing the intercept, right? Right? Yeah. But no, we cannot compare the R-squared values for the models with intercept and the models without intercept. They're completely different animals. So the R-squared values are not comparable. So avoid comparing. The reason is that when we remove R-squared, when we remove the intercept, we are inflating the denominator in the, we are deflating the denominator in the R-squared formula. So this is the formula for R-squared. We have the explained variation, the variation explained by the model, SSM, over the total variation, the variation of the dependent variable, the total variation. And so what is the explained variation? It is the total variation minus the unexplained variation. SSE is the unexplained variation. SSE is sum of squared errors. That's what we are trying to minimize when we do OLS, when we estimate the coefficients. So that's the numerator, and the denominator is the same as before, the total variation. So of course we can just take this SST out, and it becomes 1 minus SSE over SST, the unexplained variation over the total variation, and it equals to 1 minus SSE, sum of the squared errors for delta y's, and over SST, the variation in the dependent variable, which is related to the variance. The variance of the dependent variable would be this over n minus 1. So the variation divided by n minus 1 would be the variance of the dependent variable, sigma of y. So what happens is that R-squared will be inflated artificially when we force the intercept to be 0, because the SST actually is deflated. SST becomes lower. So now it's going to be up to you. Which model is better? You cannot decide based on R-squared. You have to decide based on some reasoning, based on theory, and based on some intuition. In my opinion, the blue line is the better one, the one that passes through the origin. And I provided you with the reasoning. When we have the expected number of packages to be 0, and the expected number of packages is 0, I expect to see the total number of packages delivered to be 0. So I think no intercept model would make more sense. Okay. So here is another example. We have the height versus weights of some middle school students. Okay, and we are trying to predict weight by height. We get this line here. As you can see, the line is actually, this is the blue line. The line goes down like this, and the intercept is minus 114. How would you interpret this intercept? Minus 114. What does this mean? What does this intercept mean? It means if the height of the person approaches 0, their weight approaches minus 114 pounds. Essentially, they will repel gravity. They will just fly out. So, does it make sense? No, negative weight doesn't make any sense. So probably it would make more sense to say when the height approaches 0, the volume approaches 0, and therefore the weight would approach 0. So this line would probably make more sense theoretically. However, in most of the cases, we keep the intercept, even if we don't have any good interpretation for the intercept, because having the intercept, including the intercept, helps estimating the coefficients better. And usually, the model with the intercept is a better model. So in this class, we always assume that we have intercept unless stated otherwise. So the default assumption is that we have intercept. Okay, let's go to R and see how the code looks like when we run the models. So when we have, so first of all, let's read the packages.csv. Let me try to read this data set first and see what happens. Okay, I get this error. Why do I get this error? Oh. It's weird. I don't know. How long has it been like this? Okay. I have no idea why. Oh,
So you've extended displays instead of mirroring.
yeah.
Do you know how to fix that?
Yes.
Okay. I'll be back.
Yeah. Press that accident. Yeah. So let's read the packages.csv dataset. Okay. So to do that, first we should change the working directory. Go here, set working directory, choose directory, and we go here, course data, select the course data, and now we read the packages.csv. The question? So we have 730 rows and 16 columns as before. The columns are here. We already know about the columns. Let's plot the expected packages delivered versus the packages delivered. This is the expected packages delivered versus the packages delivered. This is the diagram that I showed you before. Just use this plot command for that. Let's make the regression with intercept. The regression with intercept would be this. And let's see what's the result. This is the regression with intercept. So we have actually two coefficients here. I'm going to run it again. Two coefficients, one intercept and one coefficient for the predictor. Now let's see the regression without intercept. We force the intercept to be 0. I run this and then I run the sum. So I see we have just one coefficient, and that coefficient is the coefficient for the predictor. This is the coefficient. So it just uses the plural for coefficients, but that's fine. You have just one coefficient, as you can see here. Okay, so we are done with this. Now let's go to the next topic, assumptions. Okay, so when we use multiple linear regression, when we are estimating the coefficients and we are testing the hypothesis about coefficients, we are making several assumptions. The 5 most important assumptions are here. Good linear model. Good linear model is the first one. No perfect multicollinearity. The next one, independence of the errors and homoscedasticity or no heteroscedasticity, and then the normality of the distribution of the errors. There are some other assumptions as well, but these 5 are the most important ones. For example, heterogeneity is also another assumption. But for this class, these five assumptions would be enough. So why are these assumptions important? First of all, the distribution of the errors can affect the estimation of the p-values. We may get good estimations of the coefficients. However, when we want to test the significance of the coefficients, we need to estimate their p-values. And their p-values should be estimated based on some assumptions about the distribution of the coefficients. And the distribution of the coefficients are based on some assumptions about the distribution of the errors. And by the distribution of the coefficients, I mean, what would be their standard deviations and what would be the probability of, type 1 error and P1 and the p-value. So we need to make an assumption about the distribution of the coefficients. So to be able to calculate the p-values. And for that, we need to have some distribution for the errors and the dependent variable. And sometimes, if we violate some of the assumptions, we actually get wrong coefficients. For example, the linearity assumption is very important. If we violate that, we get wrong coefficients, wrong estimation for the coefficients. So let's go for the first assumption, good linear model. What do we mean by good? What do we mean when we say a good model? Good means that we have all the important independent variables in the model as predictors. And we do not have any extra unrelated independent variable among the predictors. Okay, we don't want to have irrelevant variables as predictors in the model. It would just contaminate the results. It would just introduce noise. And sometimes they may become significant just by chance, just by accident. It is possible. Just put 1,000 random variables in a model, and some of them may become significant. So you want to avoid introducing too many variables to the model. On the other hand, you want to include all the important variables in the model. So that's about good. When we say good, that's it. The right set of independent variables. That means good. What do we mean by linear? By linear, we mean the relationship between each independent variable and the dependent variable should be linear. So each predictor should have a linear relationship with the dependent variable. Otherwise, we cannot make a linear model. So the linear model is based on the assumption that the dependent variable has a linear relationship with each of the independent variables, with each and every of the independent variables. So how can we check for linearity? That's very straightforward. Let's use the packages dataset as before and see what are the relationships between the dependent variable, average hours per driver, and the independent variable, percentage of our size packages. As you can see, it is increasing. When we have increasing trend or a decreasing trend, we can assume linearity like this. Yes, we can assume linearity. We are not observing any pattern that contradicts linearity. Or the relationship between the dependent variable, average hours per driver, and the other independent variable, weather conditions, is decreasing. So there is a decreasing trend. So it is linear. You can assume that it is linear. There is no contradicting information here. You don't see any contradiction with linearity. So is it a linear model? Yes. But what if there was this relationship? So for example, between crop yield and average summer temperature, we observe this relationship. When the temperature is too high, the crop yield will be low. When the temperature is too low, again, the crop yield will be low. But when the temperature is moderate, we have the highest yield. So do you see an increasing trend? No. Do you see a decreasing trend? No. It first increases and then decreases. Is it a linear relationship? No, it's non-linear. It's not linear. So what can we do in these situations? There are many approaches, but the most important approach is to include a function of the independent variable in the model. So we generate another independent variable out of the one that we have. For example, in this case, we can include x2 also in the model. We have x, we include x2 as well. So we have two predictors out of one independent variable, something like that. And the model will still be linear because the equation will still be linear. We are estimating the coefficients. Just one variable will be a square of another variable. So, but don't worry about it. There will be no question in the exam about this, but just keep that in mind. You can derive some variables from other variables and have more complex equations. The second assumption is no perfect multicollinearity. So we talked about multicollinearity on Monday, and we know that if the correlation between two of the independent variables is 1 or -1, that means one of them is a function of the other, is a linear function of the other. Generally, if one of the independent variables is a linear combination of one or some of the other independent variables, that means one independent variable at least is redundant. We don't need it, and we should remove it. So we should remove the redundant independent variables from the model. If we have perfect multicollinearity, or we have just the correlation of 1, what happens is that the R program or any other program cannot decide how much coefficient to give to each of the variables, because it is essentially trying to break down one coefficient into two parts for two variables that are the same. And generally, we have to avoid perfect multicollinearity at all costs. We cannot have perfect multicollinearity. But generally, we want to avoid a strong multicollinearity too. We prefer not to have a strong multicollinearity either, because when we have a strong multicollinearity, that means some variables provide the same information. Variance is information. And when they share variance, that means they are providing the same information. The information that they're providing overlap, or let's put it this way, they explain the same part of the variance in the dependent variable. The same part of the variation is in the dependent variable. So remember, we want to explain as much of the variation in the dependent variable as possible. But if they are explaining the same part of the variation, they are not making distinct contributions. We want them to provide distinct information and make distinct contributions. So what we can do is that we can remove the redundant variables. In case of perfect multicollinearity, we have to remove the redundant variable. In case of strong multicollinearity, we prefer to remove the redundant variable, depending on how much it affects our model and depending on the context as well. So this is an example. We have the employees data set, and we have several variables as independent variables here. As you can see, we use cbind to put some variables together and make a data frame out of several independent variables. So we have technical years, current salary, etc., etc. We have these columns, we put them together in one data frame, and then we fit this data frame to the core function, correlation function, and the correlation function will give us the correlation matrix. Okay, so this is the correlation matrix that results from the command that I just showed you. So do you see any perfect multicollinearity here? Any perfect multicollinearity? We see correlation of 1. But the ones that we see are the correlations between the variables with themselves. Of course, a variable is perfectly correlated with itself. So ignore the diagonal elements. But what the other correlations? The off-diagonal elements. There is no one. There is no correlation of one. So there is no perfect multicollinearity. Okay, so we can run the model. That's for sure. Is there a strong multicollinearity? Correlation of more than 0.5. Go ahead.
Yes, between salary
Between salary and tech. That's right. What else?
salary years.
Salary and years. That's correct. What else? There is no other. There is no other. What about medium multicollinearity? Go ahead.
Well, quite a few. We have few with years. Third with years. Medium with salary.
Peers with salary. We have years with peers, cert with years, you with salary. You're right. So we have several medium multicollinearity cases. And the conclusion is what? What would you do in this situation? Salary is strongly correlated with two other independent variables. It's also correlated with some other variables. I think the independent variable salary has a lot of overlap with other independent variables. Probably we can just remove it from our model. We are not going to lose much. R squared will not decrease much. So try this at home and see what happens. Okay. The next assumption, independence of errors. So remember when we talked about the distribution of the errors and distribution of the coefficients, we assumed that the rows are independent, the observations are independent. Essentially, we are assuming that the rows in the data set are independent from each other to have independent errors. In multicollinearity, we are assuming that the columns are independent from each other. So to have independent variables. So the independent variables should be independent from each other. No correlation or small correlations. But in independence of errors, we should have the rows independent from each other. There are 3 tests for that. One test is just intuition. We just think about the possible things that can happen to the dependent variable. Can the GPAs of the students be related? Can the packages delivered be related from one day to another? For example, in one day, if I deliver a lot of packages, probably the next day I don't have as many packages to deliver. So the days that we have too many packages delivered, probably the next day we have the next days we have a small amount of packages delivered. So there can be some relationships like that, and could the observations be related from in the seasons or in a time trend or something like that? Like we know that in different seasons we have different trade volumes, you know. So that means there is some information there, and we should capture those information with independent variables, with predictors. So if we have error dependency, that means we are missing some predictors in the model. We are missing some important independent variables. and that violates the first assumption, good model. In a good model, we should include all the important independent variables in the model. If we observe a pattern in the errors, that means there is some predictor that we have missed. We have missed in the model. So let's look at the packages model. The dependent variable is average hours per driver, and independent variable is percentage of packages serviced. When we look at the scatter plot, we see that we have this linear relationship, and the errors are like this: the actual values minus the predicted values. Just as a reminder, that's the definition of error. It is delta y. What we want to see is that the delta y's be independent from each other across different regions of y. So ideally, the errors should be just noise. There is no pattern left to explain. There is no pattern left. We captured all the patterns through different predictors. So what we can do is that we can get the residuals from the fit variable. So you know, when you run the regression model using LM, using the LM function, the LM function returns a data frame, a very complex data frame. We put it in some variable, let's call it fit, and it has a lot of information, all sorts of results. One of the results would be the residuals. So if we use $resid, it gives us the list of residuals. Okay, and here we have the list of residuals. We can plot the residuals like this. We just plot the residuals against the index, just the order that they appear in the data set, and see if there is any pattern. So in this case, there is no pattern. It's just noise, random noise, pure randomness. And that's good. That means we have captured all the important predictors. No violation of the independence of errors. The third test for the independence of errors is autocorrelation. This test is important only for time series, if we have a time series. If we don't have a time series, this test is not valid, it's not relevant. So what is autocorrelation? Let's talk about autocorrelation. What is the correlation between a variable and itself? We have the dependent variable and the dependent variable, y and y. What is the correlation between y and y? What is the correlation between a variable with itself? One, that's correct. So what's your name? Tony. You get a bonus. So we call this lag of zero, variable with itself. What about the variable with one step lag? We call it lag one. Just move the rows one below, one down. Move the rows one down. So the correlation between today's and the next days. You know? The same way you can define the correlation between the day and the next 2 days. You know, lag two. So the correlation for lag zero is 1. Of course, we know that. But what is the correlation for lag 1? What would be the correlation for lag 2? That's the question. And they are important. So to see the correlations, we can just use the ACF plot or ACF function. So we just use ACF of the residuals. So you can get the residuals using $ resid, and you can plot the correlations using the ACF function. The correlations would be like this. As you can see, the first one is 1. That is lag of 0. The next one will be the correlation for lag of 1, which is very small in this case. And then the next one, smallest one. So generally they are small, except some randomness. Randomly, the 9th lag of 9 is slightly larger, but it is expected because of just randomness. So that means what? There is no autocorrelation. In this case, there is no autocorrelation. All right? No violation. So the data is not correlated with itself from the previous day. But what if the autocorrelation plot was like this? See? The correlation with the next day would be more than 60%. That means a large correlation, significant correlation. And that means what? It means this is not good. We have autocorrelation. So when the correlations after the first one, after lag of 0, are more than the value or beyond this dotted line, that means we have autocorrelation. We have autocorrelation problem. But of course, the first one, the first one is of course 1 all the time. The second one, or lag of 1, is the most important one. If this is more than the dotted line, and then the next one is more than that, that means we have autocorrelation. We definitely have autocorrelation. And what if the first one, I mean lag of 1, the first one after lag of 0, the first one is less than the dotted line, is below the dotted line, we usually don't look at the next ones because they can randomly just exceed the dotted line, and that doesn't mean much. It doesn't mean autocorrelation. Primarily, we look at lag 1. So they call it Dubin-Watson test. But when we look at all the lags, so it's a different test. So we focus on Dubin-Watson test. So here we are violating the independence of errors because we have autocorrelation. What can we do when we have autocorrelation? What's the solution? What's the remedy? First of all, we can use bootstrapping to estimate the coefficients and estimate the p-values. We're going to talk about bootstrapping later. The better approach, in my opinion, is to use the lag of a predictor in the model as a predictor. So we have x and we have x prime also in the model, in which x prime is x lagged. The lag of a predictor in the model, and the lag of the dependent variable as the predictor. So we have x and we have y prime or y minus 1 as a predictor. So we have the dependent variable y. That's what we want to predict. But we have several independent variables, x1, x2, x3, x4. We can introduce another independent variable or a predictor to the model by lagging the dependent variable. So let's name the lag of one day lag of the dependent variable, or y minus 1, y index minus 1, y of minus 1. We include that in the model, and generally that would be a known information to make prediction. So we know the value of the dependent variable the day before, essentially. So if we include that in the model as a predictor, then we can just make a better prediction for y. Again, this is a pattern. Autocorrelation is a pattern. And that means there is a predictor that we did not capture. There is an independent variable that is missing in the model. And in this particular case, the independent variable is the dependent variable with 1 day lag. And if we include that in the model, not only we are going to fix the violation, but also we are going to make a better prediction, right? So we are going to improve our predictive power. Good. Any questions so far? So the next one is homoscedasticity, but let's switch gears and go to R and see what we observe in R for a second. So I want to make sure that you understand what I taught so far. And I'm gonna go here, stop. Where is that? Oh, okay, so I have to find it. Let me just okay, let me finish the PowerPoint and we are gonna come back to R. I don't have the script here. So actually I can show you how to find the script. That's actually a good part. So you go to the second module. At the end of the second module, you go to the second module. At the end of the second module, you see assumptions.r. You just download it, and assumptions.r. Grab it and put it on desktop. So I have this script here. And let's go here, open assumptions. So we have the first assumption was good linear model. So I want to load packages.csv. Okay, I have to change the working directory, Ctrl+Shift+H. I go to desktop, course data, and then I run it again. 730 by 16. Plot percentage of hardware size versus average hours per driver. Yeah, it's linear. The next plot would be weather conditions versus average hours per driver. Again, seems to be linear. I don't see any problem here. And now let's see the regression. Average hours per driver versus percentage of hour size. Then we get the regression. We can find the residuals. So, you know, the output of the regression model would be in a variable, in a data frame. It is a data frame. We call it fit here. This data frame has several components. One of its components would be residuals. So fit $resid would give us the residuals. So we have the residuals here. Now let's go here. The second assumption,
would be no perfect multicollinearity. So we already analyzed this, so I'm not going to go into much detail here. Multicollinearity, let's load the data employees.csv. Dimensions 1,200 employees. It is not a time series. And we have these columns for it, 8 columns, 8 variables. We define we get the correlation matrix for the independent variables using cbind. Using cbind, we get a data frame that is composed of several independent variables. And then we apply the correlation function on the data frame, and we get the correlation matrix. We apply the correlation function on the data frame, and we get the correlation matrix. And this is the matrix that we already analyzed. I just wanted to show you how to obtain the matrix again. About the independence of the errors, again, I'm going to load the packages.csv and the regression. We have the regression as before. We have the residuals. We plot the residuals to see if there is any pattern. There is no pattern. This is the plot of the residuals, and there is no pattern. Since the packages.csv is a time series, it is a time series. Since it is a time series, we should test for autocorrelation. So I use the ACF function, and I see there is no autocorrelation because only lag of 0 has a significant correlation. The others are below or within the dotted lines. When the correlations are within the dotted lines, we are good. So next assumption is heteroscedasticity. Let's switch gears and go back to the PowerPoint. No heteroscedasticity. What is heteroscedasticity? So heteroscedasticity is about the variance of the errors, or the variance of the residuals in different regions of the fitted values, in different regions of y, or the dependent variable. So we have y, the dependent variable, and we want to predict it. And of course, our prediction will have errors. We are assuming that it has a constant error across different values. Okay? It has a constant deviation across different values, constant standard deviation. But what if the standard deviation depends on the value of y? For lower values, it is smaller. For higher values, it is larger, something like that. What if it's like that? So when that happens, that means there is some information in the variance. We are missing some variable here. We should fix it somehow. So homoscedasticity means that the variance is uniform across all the regions. But heteroscedasticity means that the variance changes. The variance varies across different regions of the Y. So this is a good example. You see, we have concerts and concert goers. And the concert goers, the fans, the people who went to concerts, they reported hearing ringing in their ears for several hours. Some people reported like 1 hour, some people reported 2 hours, some people reported 3 hours. So the number of hours that they experienced ringing in their ears apparently depends on the concert that they went to. Of course, some concerts are louder, some concerts are not. So in the louder concerts, you experience more ringing in your ears after the concert, right? But in each concert, in each of these concerts, you see that different people have experienced different duration of ringing in their ears. You see? So there is some kind of variance for each concert. It is kind of related to SSE, the unexplained variance. There is, of course, a variance that is explained and that is across the concerts, right? We know that from one concert to another concert, yeah, the average ringing hours would just be different from concert to concert. But within each concert, there is also a variation. This is the unexplained variation, right? So far, so good. It is important to note that this variation is uniform across different concerts. So the variance is almost the same across different concerts, right? But so in this case, we call it homoscedastic, roughly equal variance across concerts. Of course, it is subjective, but generally we can tell that the variance does not change much. But what if the diagram was like this? In one concert, we had this average. Not only the average changes from concert to concert, but also the variance changes from concert to concert. In some concerts, the variance is much larger. How would you explain that? So the unexplained variation changes in different regions, changes from concert to concert. So the unexplained variation has its own variation, has its own unexplained variation. So it is unknown, right? So it also varies, and we don't know why it varies. This is called heteroscedasticity. So, and in these cases, we have a problem. Especially, we cannot estimate the p-values. The p-values are not going to be accurate. So, how can we test for heteroscedasticity? One approach to test for heteroscedasticity is to plot x versus y for every independent variable x, just like what we did for the constants, and see if the variance is distributed equally, distributed uniformly across different values of x. So let's look at another example, the taxi data set. In this example, we want to predict the tip. The dependent variable would be the tip. And the independent variables are credit and duration. So the tip depends on credit. Credit is a binary variable. You have a binary predictor. And the scatter plots for binary predictors look like this most of the time. You see, because we have just two values for the independent variable. So, is it homoscedastic or heteroscedastic? Who says it is homoscedastic? Raise your hand. Who says it is heteroscedastic? Raise your hand. Okay, good. So it's heteroscedastic. You're right, because the variance changes. What about this one? Tip versus duration. Who says it is homoscedastic? You raise your hand. Who says it is heteroscedastic? Raise your hand. Yes, you're right. It is heteroscedastic. The variance changes. The variance is much larger for lower values. So we are violating the assumptions. There is another way to test for heteroscedasticity. The other way to test for heteroscedasticity is through making the plot, the scatter plot of the fitted values versus the residuals. So essentially, we are trying to find patterns in the residuals versus the fitted values. So what we do is that we plot the residuals. We get the residuals from the fit data frame versus the fitted values. So fitted is another component of the output of the LM function. The LM function has the output of the LM function has many components. One of them is resid, the list of residuals. The other one is fitted, the list of predicted values for the dependent variable. So we can make a scatter plot of the residuals versus the predicted values and see how it looks like. If it looks like this, that means it is heteroscedastic. We already tested this model and we already know that it is heteroscedastic. And so now you know that what a heteroscedastic model or data looks like. So you see a pattern here. The data points are concentrated in some areas and are not distributed uniformly, right? So we see the violation. Ideally, in homoscedastic situations, we should see something like this. The data points should be spread all over the place, right? No pattern, no pattern. Pattern is not good. Pattern is good if we detect it. Pattern means uncounted for variables, missed variables. There is a variable, there is a predictor, there is an opportunity that we have missed. There is an important predictor that we are missing in the model. So this kind of scatter plot would mean no heteroscedasticity. So when we have heteroscedasticity, what can we do? Again, one approach is to use bootstrapping. I'm going to talk about bootstrapping at the end of the class. But the other approach would be OLS. Just so far we used OLS, ordinary least squares. WS means weighted least squares. We weight some data points higher, larger than the other data points. So we weight some data points heavier than the other data points. And we give weight to the data points based on some formula. There are other approaches as well. So for example, taking the logarithm of the dependent variable sometimes helps. That's about it. Let's go to the last assumption, the normally distributed errors. So remember when we tried to estimate the p-values, what do we need to estimate the p-values for the coefficients? We need the t-values, right? How can we get the t-values? We get the standard deviations. Of course, we have the standard deviations and we have the coefficients. But with the coefficients and the standard deviations, we divide the coefficient by the standard deviation to get the t-value. So we're assuming that the coefficient follows a t-distribution. Essentially, you're assuming that the errors follow a normal distribution. The coefficients would follow the t-distribution if and only if the errors follow a normal distribution. So if the errors or the residuals do not follow normal distribution, then we don't know the distribution for the coefficients. the coefficients are not following the t distribution, then we cannot calculate the p-values as before. We do not have t-values anymore. The coefficients are as good as before, so we can still estimate the coefficients accurately as before. The coefficients are as good. There is no problem with the values of the coefficients. The estimated values of the coefficients are good and intact. However, when we want to test for their significance, we need p-values, and we need some distributions for them. And we don't have any distributions for them if the errors are not distributed normally. So that's why normal distribution for the errors is important. That's because of the type 1 and type 2 errors. So when the errors are not normally distributed, we may overestimate or underestimate the p-values, and therefore we may be subject to type 1 or type 2 errors. So there are 4 tests for normal distribution. All 4 are visual. The first 2 are based on the histograms. We can make the histogram for the dependent variable or the histogram for the errors. Of course, I prefer the histogram for the dependent variable because you can get the histogram for the dependent variable without running the regression. Just before running the regression, you just make the histogram for the dependent variable and compare it to the normal distribution and see if it is normal. But to make the histogram for the errors or residuals, you need to run regression and obtain the residuals. So it doesn't make sense to go for the second one. You just make the histogram of the dependent variable. For example, in the packages data set, you can make the histogram for the dependent variable average hours per driver using this command, hist of the average hours per driver. Also, if you insist on doing it after the regression analysis, you can just obtain the residuals from the regression results with $residue and make histogram of the residuals, hist of residuals. And these will be the histograms that we are looking for, the histogram for the dependent variable and the histogram for the residuals. As you can see, both of them look like normal. And they should match, essentially. If one of them is normal, the other one should be normal too. So there is one problem here, and that's it is too subjective. You know, you have to judge if it is normal, if it is not normal, you know, and it is not a good way to test rigorously. So there is a better way to test. The next 2 tests would be based on QQ plots. So instead of histograms, we use QQ plots. Again, we can make the QQ plot for the dependent variable y or the QQ plot for the residuals. Of course, I prefer y. I prefer the QQ plot for the dependent variable because you can do it before running the regression. So to make the QQ plots, you use the QQ norm function and the QQ line function. So you use QQ norm of the dependent variable and then QQ line of the dependent variable. So the first one just uses quantiles to put the data points with respect to the normal distribution. The second one, QQ line, just makes a normal distribution and draws a line for normal distribution, assuming that its average, its mean equals the average for average hours per driver, and its standard deviation is equal to the standard deviation for the data that we fed it, average hours per driver. So it takes that average hours per driver just to extract the mean and the standard deviation. That's it. It just needs two values to make the line. And that line would be perfect normal, would correspond to perfect normal. So the first one would be the QQ plot, the second one would be the reference line for normality, for perfect normality. And the same way you can just make the QQ plot for the residuals. QQ norm, $50 on resid, and QQ line, $50 on resid. So these would be the results. As you can see, they are very close to normal distribution, and you can see that we are not violating the normality assumption. What if we violate the normality assumption? What happens is that we can just take the natural log of the response variable, or y, and run the regression on log of y instead of y. And many times, in many cases, it actually just fixes the normality problem. But if it doesn't, you can use the Box-Cox transformation method to just transform any distribution to normal distribution. So the Box-Cox transformation can just transform any distribution and normalize any distribution, essentially. Another approach is to use bootstrap. I'm going to just talk about bootstrap in a minute, but before that, let me summarize the assumptions. Good linear model is the first assumption. To test for linearity, we just plot the dependent variable versus the independent variable and see if it is just increasing or decreasing, and it has just a uniform trend. It has a one-directional trend. To test for multiple linearity, we just use the correlation matrix. For the independence of errors, we use intuition. We plot the residuals, see if we can detect any pattern. And for the time series, we use the ACF function to test for autocorrelation. For homoscedasticity, we use the plot of the independent variables versus the dependent variables, so the scatter plots, and see if the variance changes over time or in the diagram. Or we can just plot the residuals versus the fitted values or the predicted values and see if there is any pattern. There should not be any pattern. And for the normal distributed errors, we can use the histograms or the QQ plots. Okay. So what about bootstrapping? So bootstrapping, I just explained to you in like 30 seconds. In bootstrapping, what we do is that we use the data and we extract a subset of the data to estimate the coefficients, like 1,000 times. So we take one subset of the data, estimate the coefficients, and take another subset of the data and estimate the coefficients. So we do it 1,000 times, and the coefficients would be estimated 1,000 times, and we get a distribution for the coefficients this way. Essentially, we are not making any assumptions about the errors or the dependent variable, the distribution of the errors or the dependent variable, and we get just a distribution for the coefficients. Of course, it is not going to be T distribution. It is not going to be T student distribution anymore, but it is going to be a known distribution, almost numerically known distribution. We have its distribution, and then we can use that numerically calculated or numerically obtained distribution to get the p-values, to calculate the p-values for the coefficients. And that's about it. So any question? Any question? Thank you.